Welcome along to this next session in this series called Exploring the Solar System. My name is Dr. Alan Wood and I'm a senior lecturer in the team at Nottingham Trent University. So, what have we been talking about so far within these sessions? Well, we've been talking about the basic patterns that are observed in the night sky. These have been observed for thousands of years. The sun rises in the east, ascends in the sky, sets in the west. There's a yearly pattern to the maximum elevation of the sun. It's different from summer to winter. The stars are in apparently fixed patterns, rotating around an apparently fixed point. And there's an annual pattern of the orientation of the constellations at midnight. And astronomy is fundamentally an observational science. These observations of the objects in the sky is what drives it. But it's supported by modelling. We need to have a model to interpret these observations. And what we were talking about last time was Ptolemy's Earth-centered model, where he thought that the Earth was at the center of the universe. And there were observations of wandering stars, of planets, which needed to be explained. And how were these explained? Well, the planets show retrograde motion. They move one way across the night sky and then the other compared to the distant, apparently fixed stars. So they go this way, then that way, then this way. And how did Ptolemy's model explain this? Well, he imagined the planets go around the Earth on transparent spheres attached to these by off-center wheels. He had a sphere for each of the objects he felt were going around the Earth. And it looked a bit like this. So here, as we saw last time, is the example from Mercury. So here we go. So here is Mercury on its epicycle, and its epicycle is attached to deferent, and that's going around the Earth. And these two things in combination give a pattern rather like this here. And the thing is, one of the big strengths of his model was observations and theory agreed. And in some ways, it was very natural to come up with an Earth-centered model. The Earth appears to be fixed and solid. It's the lights in the sky that appear to move. Ptolemy did actually consider a heliocentric, that's the sun-centered model, which he rejected almost at once. Why did he reject these? Well, equations from Aristotle implied that if the Earth was rotating, there would be huge winds going ripping past the surface of the Earth, and that's not what was observed. Now, why did Aristotle come to that conclusion? Well, he came to that conclusion because Newton had yet to revolutionize our ideas of motion. That was something that came thousands of years later. So Ptolemy considered a heliocentric model and rejected it based on the theory at the time and observations such as there were not colossal winds observed at Earth all the time. So there were some sensible ideas that went behind this. It does also show you can have lots of sensible ideas and still be wrong. But the spirit of inquiry is fabulous. Now, as time went on, better and better observations were made of the motion of the planets. And Ptolemy's model had to be modified in order to get theory and observations to agree. Minor epicycles, which rotated in the opposite direction to the epicycles, were introduced. Eccentrics were introduced, those were deferents that did not have the Earth at its center. Equants were introduced, so these were deferents with non-uniform speeds of rotation. So as you can see, this model got more and more and more complicated. And then in 1543, Copernicus proposed a heliocentric model. What was the motivation behind this? Well, Ptolemy's model had become incredibly complicated with all these additions and refinements to it. And the thing is, it can be modified in several different ways to match the same observations. And so Copernicus felt, well, if it can be modified in this way, it matches the observations. If it's modified in this way, it doesn't. If modifying it in this way is incorrect, with all the same theory behind it, or maybe all ways to modify it are incorrect. And so it was no longer an elegant model, and Copernicus proposed a sun-centered model. So what happened in Copernicus's model? How did it explain retrograde motion? Well, now what we've got is we've got the sun here at the center. Now, in Copernicus's model, the sun was not just at the center of the solar system, but at the center of the universe. So here we've got the sun in Copernicus's model at the center of the universe. The green dots here shows the Earth, the red dot shows Mars. And what happens as these planets move? Can they explain the retrograde motion of the planets as seen from Earth? Well, let's see what happens. Over time, the Earth and Mars move like this. And therefore, if you observe Mars compared to the distant, apparently fixed stars, we can see it seeming to move. And have a look at this with the orbits. Mars appears to slow down, then to go the other way, showing retrograde motion, then to slow down again, and then to move in prograde motion once again. And so Copernicus's model could explain the motion of the planets. But there were problems. The first problem is a stick falls to Earth. Something falls to Earth unless supported. So what was supporting all these objects? Why wasn't the Earth falling into the sun? Newton had yet to revolutionize ideas of motion. Now, no parallax was observed for distant stars. So parallax would mean that the stars appear to be in different positions relative to one another at different points in the Earth's orbit. This wasn't seen at this time simply because the stars were too far away to exhibit it, but nevertheless, because it wasn't known the stars were too far away to exhibit it when using just naked eye observations. This was a really good scientific objection to Copernicus's model, because Copernicus's model said the stars should seem to move relative to one another, and that's not what was observed. Also, there was an anonymous foreword put into Copernicus's manuscript by the publishers. This anonymous forward basically said, everybody knows that the Earth is at the center of the universe. Everybody knows that. However, for the purpose of this manuscript, let's pretend it isn't. Let's pretend the sun is at the center. And we're going to use that as a calculating tool. And it's just a calculating tool to help us predict the motion of the planets. Everybody knows that the Earth's really at the center. And curiously enough, that anonymous forward from the publishers meant it took a while for Copernicus's ideas to become recognized as a scientific theory rather than just a calculating tool. But here is the really, really big objection to Copernicus's model. It didn't work as well as Ptolemy's. Ptolemy's model was better at matching up theory and observations than Copernicus's. And that was a really big, serious objection. Now, in 1610, or from 1610, observations were made that started to support Copernicus's model. And Galileo observed the phases of Venus. So what he was able to observe through his telescope was that just as the moon has phases as times of being a crescent, of being half, of being full, so does Venus. And that could be explained based upon the Copernican system, where you've got the sun, Venus goes around the sun, and the Earth goes around the sun as well. As shown in this diagram here. So that supported the Copernican model of the universe. And incidentally, Giordano Bruno thought, well, if there's all these planets that we can see going around the sun, maybe the other stars are other suns, and maybe there are a large or maybe even infinite number of worlds. And so that is where we're going to finish at this point. In terms of when Copernicus's idea really took hold, well, that had to wait for the observations of Tycho Brahe and Johannes Kepler's interpretation, and that's what we're going to talk about next time. So thank you very much for your attention, enjoy the rest of your day, and I hope to see you in the next session.